All right. In the last video, we looked at our 2x2 matrix, the taxonomy of goods. And we said we have excludable, oops, we have rival on the horizontal axis, non-rival. We have excludable and we have non-excludable. And we said when we have rival and excludable goods, we call these private goods. And this is what we spent most of our time talking about in this class, and we'll return to next week. We also have non-rival but excludable goods, and we call these club goods, otherwise known as natural monopolies. And we'll talk a little bit more about monopolies next week, and you can keep natural monopolies in the back of your mind. In the last video, we talked about non-rival, non-excludable goods, which we called public goods. In this video, we're going to talk about the last of the four, common resources. All right, and in the process, we're going to introduce some baby game theory. Okay, so to set this up, we need to remember a bit about the Freerider problem. And the Freerider problem essentially says we have a problem when my use doesn't cost me anything. In the context of public goods, because me using a public good doesn't hurt others who also want to use it, we get this under provision of public goods. Our socially efficient quantity is beyond what the market will allocate. So we got this result where the socially efficient level of public goods is much larger than the market provision of public goods. And so we talked about solutions potentially to public goods problems. Here, the Freerider problem is more pernicious. With common resources, they are both not excludable, as public goods are not excludable, but common resources are also rival. So my using them affects you, where with public goods, my using them did not affect you. So the Freerider problem here becomes even more problematic. So we'll just leave this floating in a little box up at the top. All right, so to set up how common resources have classically been modeled, let's look at a little pond. Okay, so we have our pond, and we're going to draw a little goldfish. I'm getting a PhD in economics, not art. If I had a laugh track, this is where I would turn that on. Okay, so we're going to start off looking at two individuals. So we have individual 1, Y, and individual 2. Let's give them a name. Yuri and individual Z. And we'll call them Zeta. Okay. Now, Yuri and Zeta are hanging out at this lake. And they both fish, and they both receive income from fishing. So fishing is a very important part of their livelihoods. The more fish they harvest, the better off they are. But every year, the number of fish in the pond doubles. And you can sort of think of this, there are population models which I can draw here. So we get these like petri dish models with the sigmoid function. I'll refer you to the internet for better sources than myself. But essentially, what we're saying is over time, the number of fish in the pond is going to double. So let's say Uri and Zeta are each harvesting 2 fish every year. Let's look at one case. So at the end of this year, because Uri is harvested 2 and Zeta is harvested 2, we have 5 left over. But because we have 1, 2, 3, 4, 5. So because the fish are doubling every year, next year we're going to have 10 fish. If Uri and Zeta both harvest 2 fish next year, that leaves us with 6 fish times 2. It's going to give us 12 at the end, sort of year 3. So it's year 2, year 3. Okay. But let's say Zeta decides, okay, this is great. Our population of fish is increasing. What's good for me is to harvest another fish this year. I'm imposing an externality on Uri because we're going to be slowing down the doubling rate, right? And the number of fish in the pond is going to go down. But it's good for me. I'm going to harvest 3 fish instead of 2. Uri can't stop me, so I'm just going to harvest. It's good for me in the short term, and I'm imposing an externality on everyone, but mostly on Uri in the long run, because I'm going to be benefiting most from the fish. So let's go to case 2. So in year 2, we have 4 fish. Doubling gives us 8. The next year, we have 8 fish. We harvest 5, gives us 3. And multiply that by 2 to get 6. Okay, so just because Zeta is harvesting more fish, which Zeta is perfectly allowed to, given that this is a common resource, just because Zeta has an incentive to harvest more fish, the population of the fish is going to go down. And this is actually what's happening in fisheries around the world, particularly common resource fisheries, so like deep sea fishing. This example is relatively mild because in this case, Zeta is actually imposing an externality on themselves. With common resources that are accessible by many, many individuals, this Freerider problem is much more stark. The externality is almost entirely imposed on others because one individual has very little effect on the common resource. But here we can even see with this relatively mild example that Zeta's actions lead to what we call the tragedy of the commons. And we'll put this in a gloomy color. I'm not sure if this is gloomy. And the tragedy of the commons is what's happening here. The Freerider problem and the rivalry of the resource lead to over-extraction and a degradation of the commons. And you can think of this same dynamic if you've ever shared a house with housemates, particularly when it comes to kitchens. So this type of dynamic is quite common. So let's set this up in a different way, build some game theory. And we're going to talk about game theory much more when we talk about oligopoly next week. But for now, let's just set up a simple model of the tragedy of the commons. So let's say we have Zeta on the top and Yuri on the side. And let's create some abstract numbers here. So let's say if Yuri and Zeta come to some sort of commons agreement, they say we're both going to agree to not over harvest. Let's say they both can harvest a nice amount of fish every year. So let's say they can harvest 10 fish each. But let's say Zeta, let's say Zeta reneges on their agreement. So Yuri is still following through on his agreement, and Zeta decides not to. The first number is going to represent Yuri. Yuri takes a hit. Yuri can't harvest as many fish, and at the same time, Yuri isn't benefiting from the over extraction. So Yuri's absorbing all of the externality with none of the benefit. While Zeta's benefiting from the over extraction. Zeta, in this case, might be imposing some of the externality on themselves, but mostly benefiting. And so there's actually good reason for Zeta to over extract. And going back to our example with the actual pond, this makes a lot of sense, particularly when you think about situations where there are more than two individuals. But even when there are two, this applies. So let's consider the case when Yuri reneges, but Zeta follows through on the agreement. So it's going to look very similar. The first entry is going to be Yuri, because Yuri is reneging. Yuri gets the benefits of the over extraction, and all of the externalities get imposed on Zeta. But what happens when they both renege? So this is bad for everyone, and this is what we call the tragedy of the commons. So if they both renege, they're both gaining some of the over extraction, right? In the first years, they're going to be doing just fine. They're going to over extract, and they're going to harvest more fish in the first year. And then over time, the externality is going to be imposed on both of them. So it's better than having the other person renege while you agree, but it's not as good as if both individuals agreed to the non-extraction. Okay, so this is what we call a game matrix, or a normal form game. If you want to go on and do more game theory, you'll see a lot of this. So the way we think about these games, well, first off, let's identify the efficient outcome. So when we think about efficiency, we've thought about what maximizes welfare in society, and in this case, society is just Yuri and Zeta. So for this first box, we can see it's a fair distribution. Both are getting 10. And this is also the efficient outcome, because the total number of fish being harvested is 20. If we looked at either of the others, so the off diagonals, you would see 4 and 14, and the lower right box, you'd see 6 and 6. The total number of fish being harvested is lower than 20. So we found the efficient outcome. But let's look at their incentives. So let's think this through systematically. So first off, let's think about what happens when Yuri, for sure, chooses to stick with the agreement. What should Zeta do? Well, so the way we're going to do this systematically is we're going to underline the payoff for Zeta that corresponds with Zeta's best action. So Yuri is choosing A. Zeta is making the decision between 10 and 14. So for Zeta, given that Yuri is choosing the agreement, Zeta should choose 14. So let's box this in. And let's actually do this in another color, or less gloomy red. Okay. All right, but what if Yuri was choosing to renege and Zeta knew this? What should Zeta do? Well, Zeta's given the choice between 4 and 6. So if Zeta chooses to stick with the agreement while Yuri reneges, Zeta would get 4. If Zeta chooses to renege while Yuri reneges, Zeta would get 6. So 6 is clearly better than 4, and Zeta will choose the renege. Okay, so one conclusion here. No matter what Yuri is doing, it's always better for Zeta to renege. And this is what we call a dominant strategy. A dominant strategy is a strategy that's always best, no matter what our rival does. All right. So let's walk through this same type of logic for Yuri. So let's say, and let's do this in blue. Let's say let's say Zeta is for sure choosing the agreement. What should Yuri do? Well, Yuri's given the choice between A, which gives a payoff of 10, and R, which gives a payoff of 14. So Yuri, we're going to box this. Because Yuri can get a payoff of 14 by choosing R, Yuri should choose R. So what if Zeta is choosing renege? Well, again, Yuri is given the choice between A and R. A gives a payoff of 4, R gives a payoff of 6. So Yuri should choose R. And again, this is a dominant strategy. No matter what Zeta is doing, it's always better for Yuri to choose R. And we can see this on the payoff matrix because R corresponds with both of our squared payoffs. Okay, so this gives us a useful tool, the dominant strategy. We have one more tool that we care about, particularly in this class. And it's called the Nash equilibrium. Our Nash equilibrium is a set of choices, a set of strategies. In this case, a pair of strategies where neither player wants to change. So we have a Nash equilibrium and we have a dominant strategy as definitions. We found that both Zeta and Yuri have a dominant strategy, and that's to choose R. Is there a Nash equilibrium? Well, the quick answer is yes. If both payoffs in a box are boxed, then that is a Nash equilibrium, and we'll square that in purple. So let me just reiterate that. If both payoffs are boxed using the boxing method, that's a Nash equilibrium. And also, if both players have a dominant strategy, playing their dominant strategy will give a Nash equilibrium. So the Nash equilibrium here is R and R, and this is our Nash equilibrium.